In this class, we are going to learn how we can solve a wave structure using direct stiffness method. Here, we are going to solve this problem. In this problem, we have two members. Our member one, our member two, and here 2 point load is acting. First point load here, 250 kilonewton, and here we have 50 kilonewton. Both are acting at the center point. This acting at the middle point of this same member one and 50 kilonewton force acting at the midpoint of this same member two. And here it is saying that your EI and EA both are constant for the member one and the member two. And we have to find the critical shape in the bending diagram. Now, before going to our critical shape and bending diagram, we first learn how we can solve this problem. So now, if you want to solve this same problem, recall that in beam analysis, we need to solve the force F equal to your KU times. We have to solve F that is equal to K times U plus fixed and action. This F is corresponding to the active nodal forces. The F here is corresponding to the active nodal forces. What are the nodal force acting in the particular degree of freedom? Okay, or force is acting in particular node, or you can say moment acting in particular node. This part will come is left side F. If we do not have any nodal forces, then F vector then our F vector will be 0. And fixed in action, this term will come from our applied, which is acting in the span. Here, you have some force acting here, some force acting there. So due to the force which is acting in the span, due to that force, there will be some moment, there will be some fixed in action develop the nearest node. Okay. So, what we do, we have to find a fixed in action. In the fixed in actions, we will have to consider fixed in moment as well as your fixed in forces. So here you can see we have 25 kilonewton force acting there. The force that will be your fixed end force that will act here in this direction. Okay, since this force is acting in the midpoint, so here we have 25 kilonewton force here and 12.5 force this side and 12.5 kilonewton force this side. And moment that will be your WL by 8 MR. Okay. Here W is a 25, L we have 6 by 8. So if you calculate it, it should come as your 12750 Newton meter. So here 25 you have to convert into Newton meter. So 25 kilonewton we have, so 25,000 Newton meter times 6 by 8. So if you calculate that force, that moment will come as well 18750 Newton meter. Okay. This side, the moment will be anti-clockwise. So you have to consider as a positive moment. Here, this side, the moment will be clockwise. So you will consider negative moment. Similarly, consider this force. Then the force that will develop 25 kilonewton, okay, or 25,000 Newton force, vertical forces, and moment here will act like this. Okay. Now, if we solve this equation where F force will be 0 because we do not have random forces, solve this equation Ku FEA. Okay, from that you can find how much displacement is coming. So displacement that will be K inverse times FEA. So here there will be some minus sign that you have to consider. Yeah. Okay. And if you solve it, you will get that we are getting some displacement quantity in this particular node because this n is fixed here and this n also fixed. So we will not have any displacement quantity, displacement in terms of translation and rotation. Because we will not have any displacement here and here. Okay, this part is zero displacement, only displacement that will come in this node. So in this node, you will see what are the degree freedom involved here. Once identify the degree freedom, then we can find corresponding displacement quantity. So here we get some displacement here, some displacement here, and also we'll observe there will be some rotation is coming. So we'll get some rotation. Yeah. Okay. Now once you plot it, you will get this. We put a shape like this. Here we have zero displacement, then we will go like this, and then we find like this. Here, observe to maintain this shape, this slope should be negative. The slope should be clockwise direction. So here we have to keep one thing in mind that we are considering all upward force positive, all anti-clockwise moment as a positive, and all anti-clockwise slope as positive. So this sign convention will follow throughout this example problem. Okay. Now learn that we are going to solve that if your KU plus 610 x. Okay. Now our primary job is to find our global K matrix. This part either will be given, okay, in terms of nodal forces. If not given, that means that will be 0. And this action we can calculate from our forces acting in the span. So only quantity that is unknown to us are K and Q. K we can find, the K, global K we can find once you know how to find the stiffness matrix for an element. Okay, from there we can go for assembly of the two stiffness matrix. Here we have two elements, element 1 and element 2. Once you know how to assemble the two stiffness matrix, we can find the K. And only quantity unknown is our Q. Okay. So here we learn how we can find the element stiffness matrix. Okay. Now, before going to the element stiffness matrix, we should know what is the degree freedom for a frame element. Once you identify that how many degree freedom we have for a frame element, then you can make sure the size of the element stiffness matrix will be of that size. So we have, so for example, if you have 2 degree freedom for a element that we used to have in a truss element, then our stiffness matrix for the truss will be 2 by 2. If we have 4 degree freedom for a element, then our stiffness matrix for the truss will be 4 by 4 side. Then in the beam element also we have learned we have 2 degree freedom at each node. One is corresponding to vertical translation, another is corresponding to rotation. So we have learned for beam element we have 2 degree freedom at each node. 1, 2, 3, 4. So for beam element we used to have 4 by 4 side. We used to have stiffness matrix of 4 by 4 side for a element. We used to have a stiffness matrix 4 by 4 side for a element. Now here we have to identify how much degree freedom we have, how many degree freedom we have for a frame element. Now we have learned that a truss can carry axial force. Truss we design such that it can carry only axial force, and beam we design such that it can carry the deformations to the bending. And frame element we use to model which can carry both axial force as well as bending. Okay. So now for a frame element, we should have a degree freedom which is corresponding to the axial element, as well as we should have a degree freedom which is corresponding to our beam element. Okay. Now element 1. Now the element 1, you can see what are the degree of freedom we have. What we're going to do, we're going to find the degree of freedom for the frame element. Okay. Now, if this is your frame member, so first degree freedom we'll consider acting in the axial direction. Second degree freedom we'll consider which is acting transversely. Third degree freedom we're going to consider which is corresponding to our rotation. Okay. So in one node we have 3 degree freedom, and other side again we'll have axial degree freedom, we have transverse displacement degree freedom, and we have rotation degree freedom. So here you can see for a frame element we used to have 6 degree freedom. So the size of our stiffness matrix for the frame element will be 6 by 6 size. Okay, so how to get this quantity we will discuss later. Okay, so first we identified that we have 6 degree freedom for a frame element. So our size of the stiffness matrix will be 6 by 6. Okay. Now, once we identify the stiffness matrix for a frame element, okay, then we need to assemble it if we have more number of frame elements. Okay. Here we have 2 number of frame element 1 and element 2. Okay, we'll see how we can assemble it and we can identify the global stiffness matrix. Now, if we want to find the global stiffness matrix, then we have to first identify what are the global node numbering and corresponding global degree freedom. So here, what we did, we have considered this is our node 1, okay, this is our node 2, and this is our node 3. Okay. So now we know at each node we have 3 degree freedom. Okay. So we have total 3 nodes. So total we will have 9 degree freedom for a frame element. So size of our global stiffness matrix will be 9 plus 9. Okay. Now first we have to identify element stiffness matrix and what are the components coming in the element stiffness matrix, and then we can assemble it. Here already we have discussed that if you want to obtain the stiffness matrix, what we need to do, we need to first identify the node number, and we need to identify the corresponding degree freedom. So here we have degree freedom 1, 2, and the 3, 4, 5, and the 6. Now, if you want to obtain the stiffness matrix for a frame element, what we need to do, we need to apply unit translation or unit rotation in the corresponding degree freedom, and we need to see what are the forces is developing in the other degree freedom. For example, if you want to provide unit displacement in the first degree freedom, so here we are providing unit displacement in the first degree freedom. We are going to see what are the forces is developing in the other degree freedom. Now, since we are applying pure axial displacement here, so what will happen? We will have only forces corresponding to the axial degree of freedom. We will not have any forces on the 5th degree freedom, 6th degree freedom, and here 4th and 3rd degree freedom. If we apply a pure axial deformation, if you provide pure axial deformations, then that will generate. Then for that case, we need to apply AE by L amount of forces to have this unit deformation here. Now here, if we apply this amount of force, then obviously in that other side will have same amount of force but in opposite direction. Okay, so here we are applying AE by L amount of force to have unit displacement here. And if we apply this force here, on the other side, on the corresponding to the 4th degree freedom, we will have same amount of reaction force, but in opposite direction. Okay, so now here we just see we first apply unit displacement in the 1st degree freedom, and we see what are the forces is developing. Now here you can say that force required for unit displacement is the stiffness. So here we are writing K11, that means force required at degree of freedom 1 corresponding to the unit displacement at degree of freedom 1. So that is your K11. So that is your corresponding to the first term of the Stiffness matrix K11, and that value is AE by L. Now if you want to see how AE by L term is coming, then you have to go to our class problem to see how this term is coming. Now here that K41, that is basically force that is developing at 4th degree freedom due to unit displacement at the 1st degree freedom, that is your K41. Okay, now here we can see we obtain the first column of our frame problem. So here we'll have some value K11, and at the 4th degree freedom we'll have K41. Okay, so we know the stiffness, that is your force required for unit displacement. Now for obtain the stiffness matrix, what do we do? We have to apply unit displacement corresponding degree freedom, and we have to see what are the forces developing in other degree freedom. So here we are providing unit displacement in the 1st degree freedom, and we see that what are the forces developing, and what do you observe? We observe that to have the unit displacement at 1st degree freedom, we need to apply AE by L amount of force at the 1st degree freedom. Now if we apply AE by L amount of force at the 1st degree freedom, that is corresponding to K11. Okay, now if we apply this amount of force at the 1st degree freedom, then at the 4th degree freedom we'll have the same amount of force but in opposite direction. So here if we see that 6 by 6 size of the stiffness matrix for a frame element, we obtain a first column, and here we'll have K11 term, and here we'll have minus K11, or other way you can say that K41. The minus sign is corresponding to the negative distance with respect to K11. Okay, so here you can write 1, 2, 3, and this is 4 and 5 and 6. Okay, so this value will be 0 here. Similarly, we can obtain our 4th column. So to obtain the 4th column, what do we do? We have to apply unit displacement here, and we have to see how much force is required to have unit displacement at the 4th degree freedom. And once we apply this force, what are the forces is developing in other degree freedom? So we'll observe that we're getting similar value. Okay, so K44 now will be positive value, K44 here will be positive value, and K14 will be of negative value, that is equal to minus K44. Okay. Now here you can see we obtain 1st column and the 4th column, that is corresponding to our axial degree freedom. Okay, now you want to obtain the 2nd, 3rd, and your 5th and 6th degree freedom. Then what do we do? We have to apply unit displacement or unit rotation corresponding to the degree freedom to see what are the forces developing, and like that way we can obtain the stiffness matrix for the frame element. Here you just see we obtain that our value corresponding to our first degree freedom and fourth degree freedom. Here you can see this value is symmetric in nature and diagonal term coming positive. Now what we are going to do, we are going to see how we can obtain the value which is corresponding to our second column, third column, fifth column, and sixth column. So second column, that is corresponding to the second degree freedom, that is your transverse displacement, and fifth column also corresponding to transverse displacement on the other node, and your third degree freedom is corresponding to the rotation here, and sixth degree freedom is corresponding to the rotation. Now, if you want to obtain the second column of the stiffness matrix, what you need to do, you need to apply unit displacement corresponding to the unit displacement corresponding to second degree freedom, and we need to see what are the forces is developing. Now here you will observe that if we apply unit displacement in the translational degree freedom, then in the axial degree freedom, that force that will develop will be 0. Okay, so if we apply unit transverse displacement, that will not cause any forces corresponding to the axial degree freedom. Okay, so these two degree freedom are independent to each other. So here we will apply unit displacement. Now, if we apply unit displacement, then we need to see what are the forces is developing. Okay, so to have that unit displacement here in the second degree freedom, we need to apply 12 E by LK amount in the second degree freedom. That is basically the force, that is the force developed at the second degree freedom due to unit displacement and the second degree freedom. So here the force developing the third degree freedom was from the unit displacement in the second degree freedom. So here it's observed this value are corresponding to the our stiffness matrix of the beam. Only thing is that our degree freedom has changed now. This value are corresponding to the stiffness matrix of the beam element. Only thing is that we have now changed degree freedom. Okay. So here we will apply unit displacement and we're going to see what are the forces are developing. So here what we're going to do, here what we're going to assume, we're going to assume upward forces are positive. Okay. And anti-clockwise moment as positive. And we're going to see how the stiffness matrix look like. So here we apply unit displacement in the second degree freedom. Now what we're going to do, we're going to apply unit rotation corresponding to the third degree freedom. And we're going to see what are the forces is developing. Again, if we apply unit rotation in the third degree freedom, then the axial component will be 0. The force that will develop in the axial direction will be 0. Okay, so our axial degree freedom is independent from our second degree freedom and the third degree freedom. So here, if we want to apply unit rotation, then we need to if you want to have unit rotation and the third degree freedom, we need to apply 4 E by L amount of moment the third degree freedom. Okay. Now, if we apply this amount of moment here, then at other end, the 2 E by L amount of moment will carry. Now, if we apply unit rotation here, then you observe that 6 E by L square amount force will level up in the translational degree freedom. Okay, if this is upward, and for that equilibrium conditions, you should have downward forces here. Okay. Now, similarly, we can obtain value corresponding to the unit displacement in the 5th degree freedom and unit rotation in the 6th degree freedom. Okay, so now if we see what are the forces developing, okay, you will observe that our stiffness matrix will look like this. So here you will observe this value are corresponding to our beam element. Only thing is that our degree freedom has changed now. So here, first degree and here first degree and fourth degree is corresponding to axial degree freedom. So we have some value that is corresponding to axial deformations. Okay. And consider the second column. This value is corresponding to our stiffness matrix. This value is corresponding to the stiffness matrix of beam element. Only thing is that we are keeping 0 value on the axial degree freedom. Okay, so here we just see we have filled second column and our second column and our third column, second column and third column. Okay, so initially we consider first degree freedom, so we fill first column and the first row, and then we consider fourth degree freedom, we fill fourth column and the fourth row. Now we applied unit displacement at the second degree freedom and unit rotated in the third degree freedom. So we obtain our value corresponding to second column, third column, and second row, third row. Now, if we apply unit displacement corresponding to fifth degree and sixth degree, we can fill these two columns. Now, if we apply unit displacement in the fifth degree freedom and unit rotation at the sixth degree freedom, you'll observe that we are getting the value here. So now, here we just see this is our stiffness matrix for a frame element, and the size of the stiffness matrix is 6 by 6. And first degree is corresponding to the axial degree freedom, and fourth degree is corresponding to axial degree freedom, and 2, 3, 5, 6 is corresponding to our degree freedom of a beam element. Okay, so we have this stiffness matrix for a frame element. Now here you just see in the frame element, the size of the stiffness matrix is 6 by 6 because we have 6 degree freedom for a frame element, and all the diagonal terms are positive, and stiffness matrix is symmetric. Okay. Now what are we going to do? We are going to see whether we need the transformation or not. So here you just see this is our first element and this is our second element. Second element is rotated horizontally. So theta for this case is 0. So for the second element, we do not need to apply any transformation matrix. So there is no need to apply any transformation. But first element have the rotation of 90 degree. So here we are considering this node 1 and this is node 2. So here this is our positive 90 degree. Now if you consider this is node 1 and this is node 2, then you can say this is our minus 90 degree. Okay, or other way you can say this is your 360 minus 90 degree, 270 degree, positive 270 degree. Okay, so here we are considering this is node 1 and this is node 2. So we'll have positive 90 degree angle at node 1 or at node A. Now, since this frame member, this is the first frame member inclined in some angle, then we need to apply transformation matrix. Now here we have to learn how the transformation matrix look like. How the transformation matrix look like. We have learned that for a truss element we need to apply transformation, and we also learned how the transformation matrix look like for the truss element. Now we'll extend that same philosophy for a frame element.